Everyone, and welcome back to Video at Scale. I'm Adar Solanki, and I'll be your host again today for the second and final day of our show this year. Today, we have another 6 excellent talks lined up for you, where we'll learn about things from video compression and storage efficiency, measuring video quality, and even learn some details about some exciting developments in software encoding. After the 6 scheduled presentations, we'll cap the day off with a live panel on the topic the importance of audio, covering the emergence of new audio-only products and experiences, and discussing audio-focused investments with panelists from Facebook, Google, and Netflix. A reminder to the audience, you can use the live comments to ask questions during each talk, and we'll try to answer them during the live Q&A sessions if we have time. Now, without further ado, it's time for our first 2 speakers, Shankar and Srinath from Facebook. We're going to talk about video encoding efficiency.
Hello. In this presentation, we will talk about video encoding for user-generated content. We'll share our journeys with ASICs, with RDX, and how we have come to rethink compute and compression efficiency at scale. Video now accounts for almost half of the time spent on Facebook. As most people will well realize, video transcoding is computationally very expensive, and it accounts for a major chunk of our backend compute power. With this in mind, Facebook invested in hardware accelerators for video transcoders a few years back to offload the heavy computational workloads for video processing. These ASICs are more power efficient and with a higher density, and have already helped us in getting to a more optimal operating point on the compression efficiency versus computation. The journey to onboard a new technology like ASICs is not straightforward. Taking it to production has been quite exciting, with many challenges and stumbles, ranging from quality, robustness, reliability, and from an operations perspective. However, that is a story for another time. The important point I wanted to highlight is that fixed function hardware has limits on the maximum achievable quality it can provide to a majority of our content. So how do we continue to improve the top-line quality at scale, and especially at the scale at which Facebook operates? While we ponder on that question, I'll switch to another exciting journey our close colleagues were embarking upon. If you have not watched last year's presentation by Nick Wu on convex hull encodings, I would highly recommend you do so. Let's do a quick recap of the same. RDX is not the explosive here, though it's turned out to be just as powerful for video processing. It's a technique for finding the best encoding recipes for any given video to fully optimize for the convex hull of quality and bitrate. It's a 2-stage process, let me call them L1 and L2. In the first stage, L1, we transcode an input video using a variety of resolutions and CRFs to obtain a set of different BD curves that you'll see on the chart to your left. The convex hull of this set of different BD curves, denoted by the set of points you see on the chart to your right, is the most optimal subset of recipes that we should be using for this video. And it is provably so. This technique has already been deployed in our production stack for select curated content, and back in 2020 has shown very impressive compression efficiency gains of up to 15% compared to a previous state-of-the-art. That said, it is fairly obvious that this technique is computationally very expensive. With so many different permutations to explore in L1, how can we possibly hope to scale this up? The fun did not end there. We further proved that you can leverage a much faster encoder in L1, which is the more expensive stage, and still obtain a near optimal convex hull at a significantly lower compute cost. To make it even more exciting, in the chart to your right, you'll see that you can use a different codec for L1 and still come out ahead in terms of compression efficiency, while your compute costs shrink further. For example, for a really expensive encoder like AV1, you can use a faster preset of BP9, and then the final projective convex hull is still near optimal as it would be if you had used AV1 in stage 1. Now we come back to the question, so how do we leverage this insight and help us scale up RDX to an increasing majority of our content? And that's where the ASICs come into play. By leveraging ASICs in our first L1 stage, we identified that the resulting compression efficiency wins are only 2% lower than a pure software-only convex hull that we saw a few slides back. And the net power cost is a tiny fraction of what the original approach was. And this is where we are in 2021. This hybrid hardware-software RDX is now rolling to our production, and it will become the de facto encoding technique for a vast majority of our content. This approach has helped us significantly improve the video quality that we serve to our users at scale. Looking ahead, we are exploring further possibilities to explore the right trade-off between compression efficiency and computation. We have seen that leveraging ASICs has helped us significantly reduce power. There are ongoing follow-up efforts in leveraging a faster encoder in L2 to further reduce our software power cost with an acceptable trade-off in compression efficiency, again to the tune of a couple of percentage points. And we have yet to explore a full hardware-hardware RDX, which will be a massively lower power point with a little bit more trade-off gain. But this brings us to a next interesting challenge. We can now identify a different set of options or knobs where each provides a certain improvement in compression efficiency over heuristic approaches, but each with a different operating point. How do we optimize for this at scale, especially at the scale at which Facebook operates, to identify the efficient frontier for videos scale at Facebook? I now hand it over to my good friend Shankar, who will guide us through the rest of this very insightful journey. Over to you, Shankar.
Thank you, Srinath. Next, I want to be talking about how we can optimize compute and compression efficiency jointly for user-generated content. To recap, compression efficiency is about minimizing the bitrate needed to achieve a certain visual quality. And by maximizing compression efficiency, we get less stall and higher quality of experience even in low bandwidth conditions. Further, this reduces data usage for our users, which is important in cell networks, particularly in emerging markets. And in addition to compression efficiency, the billion scale nature of UGC also dictates the need for compute efficiency. Okay, what are the challenges in doing this optimization for UGC videos? The first unique property of UGC videos is that its popularity varies widely. The chart shows the distribution of watch time of UGC videos versus the number of videos. On the left, you have the relatively few UGC videos which are very popular. They could be viral videos which can get hundreds of millions of views. And these few videos represent a lot of watch time. On the right-hand side, we have the more typical UGC video which gets relatively few views, and most of these videos represent a relatively small amount of watch time. Now, as you can see, you don't want to use the same encoder for all these different videos. But the encoder has a lot of choices. It can choose different codecs, as well as choose different presets and settings for each codec. Now, how do we choose the codec and the setting to optimize the overall compute and compression? That is going to be focus of the next part of the talk. So first, let's look at the convex cell of compression efficiency versus compute. And again, this picture shows without all of the codecs without RDX. On the x-axis, we have the normalized compute where x.264 very slow is arbitrarily normalized to a compute of 1. That means a codec which is like as a normalized compute of 10 has 10 times more compute than x.264 very slow. On the y-axis, we have the normalized compression efficiency where again x.264 is normalized to 1, which means a codec which has a normalized compute of 2 has 50% lower bit for the same quality. As you can see from these charts, within each codec, as you spend more compute, you get higher compression efficiency. And at the same time, as you move to more advanced codecs, you get higher compression efficiency at the same compute. We just saw that newer codecs have higher compression efficiency at the same compute. So can we look only at newer codecs for our optimization? No. This is because Facebook videos are viewed on a variety of platforms, and newer codecs are not supported on all devices. Therefore, for a video for which we produce, say, VP9 or AV1 encodings, we still need to produce and deliver H.264 encodings for those devices which cannot support advanced codecs. That means, for compute compression efficiency trade-offs, it is important to look at newer codecs as well as older codecs. Now let's look at how the convex cell evolved when we include ASIC-RDX. So here, the chart shows the compute versus compression efficiency with and without ASIC-RDX for the different codecs. As a reminder, for the ASIC-RDX, in stage 1 always uses ASIC, while stage 2 could be using either a software encoder at different preset or could be ASIC itself. As you can see, is by using ASIC for stage 1, you get the RDX compression gain with a very, very small additional compute. As a result, ASIC-RDX is on the convex hull for every codec. That means ASIC-RDX gives you the best compression for a given compute for any codec over non-RDX. Okay, so we now know the convex hull points, but the question still remains, which convex hull recipe do you want to pick for each video? Because you can vary the stage 2 recipe for each of the convex hull points. So let's make an example. Let's say for a video, we produce H.264 encodings and VP9 encodings. For H.264 encodings, let's say we picked a very slow, which would give a normalized compression efficiency of 1 and normalized compute of 1. And for VP9 encoding, let's say we picked a recipe which is 30% more efficient in terms of bits, while it is 5 times more expensive in terms of computing. Now let us say this video is viewed by our users and 80% of the devices support VP9 and H.264 is played rest of the time. Now how can we model the compression efficiency of the encodings we produce for this video? Now we can model the average compression efficiency as an average of the 80% of the time the VP9 encodings are played and its compression efficiency, and the 20% of the time H.264 encodings are played and its compression efficiency. And the compute used for producing these encodings is obviously the sum of the compute needed for H.264 encodings and producing the VP9 encodings. Now, this allows us to vary the recipe based on popularity of the video as well as the codec support and model the impact on both the compression efficiency and compute. Now let's put it all together. Our problem is one of optimizing overall compression efficiency. So we have the watch time distribution of the videos. We have the codec player support. We also know the convex hull points of compression versus compute, where we know that ASIC-RDX is always on the convex hull. And we also have the compute constraints. This is obviously a linear programming problem to maximize the compression efficiency with these constraints. And you get the recipe for each video, which maximizes the overall compression efficiency. And in this model, automatically ensures that more popular videos get encodings with higher compute and use of recipes with advanced codecs grows with the player support. And this model allows us to quickly iterate on various different scenarios, as I'll be explaining next. So in addition to looking at maximizing compression efficiency, we can look at the inverse problem of minimizing compute for a certain level of compression efficiency. On the right, we have a chart which shows how much compute we need for a given level of compression efficiency, both with and without ASIC-RDX. And as you can see, for any given level of normalized compression efficiency, ASIC-RDX gives us significant compute savings over non-RDX. And this model can account for variations in player support for codecs, watch time distribution changes, as well as efficiency improvements both in software and ASIC. But the conclusion remains, ASIC-RDX provides significant compute savings to achieve same compression efficiency, and this conclusion is robust to all these different variations. So what are the takeaways here? The first takeaway is optimizing compute and compression efficiency jointly is a must, so that we can ensure that videos remains and continues to remain a high quality experience for everyone in the world. And at the same time, we can produce the encodings needed for this high quality experience in a sustainable manner. Next, ASIC and RDX have a central role in achieving this vision. Thank you.
Wow, what a great first talk. Compression efficiency continues to be an important thing as you're delivering video at scale. And I'm lucky now to be joined by the two speakers, Shankar and Srinath. Hey guys, thanks for joining.
Thanks, Adarsh. Welcome to me.
Thanks, Adarsh.
So yeah, I think we'll just kick it off right to the audience Q&A. We have some questions here lined up. The first one is from Nicholas in the audience. And the question is, Is the compression efficiency calculation assuming the same picture quality for both H.264 and VP9?
That's a great question. So one thing is we do try to account for both picture quality and bit and the bit rate. So if you look at it, we don't actually calculate the picture quality at just one point, and so that everything has to be apples to apples. And we do know that different codecs at different presets produce different points. So we look along the whole spectrum of the curve, of the rate distortion curve, and try to understand the average delta in compression efficiency, or which is the bit rate per quality. Srinath, do you want to add anything to that?
No, I think Shankar, you covered it well. The intent is to actually span the entire available search space and find the most optimal operating point that gives us the best BD rate at any given compute. So we're trying to jointly optimize for both.
Got it. Hope that answers your question, Nicholas. The next one we have here is, what is the current deployment rate and your plan for AV1?
So first I want to, again, sort of revisit some of the history of AV1. And Facebook is one of the founding members of the AOM Alliance. And sort of AV1 has always been an integral part of our plan. And as you just saw from the, and we are actually currently even deploying AV1 at a small scale for the last few years. But to actually deploy a codec at scale for the diverse audience that we have and for the scale that we have, we need two things, as you saw from the talk. One is a wide decoder support. So that means all the mobile devices need to support a new codec, as well as really good compression efficiency, so that it makes sense to get for the same compression to compute efficiency, that being optimal. These are the sort of the two different aspects. One is decoder support, other is compression to compute efficiency points. So we are working actually and investing heavily on both ends of the spectrum. We are working on making wider decoder support for AV1, as well as investing more in increasing the compute efficiency so that it makes sense for wide deployment. Srinath, do you want to add anything to that?
No, I think the main big challenge right now is wider adoption of decoder support. I think based on our studies and even given the trend of how the AV1 encoder is speeding up, we're getting more and more optimistic about the AV on the encode side. And as we get more and more comfortable on the decode side support, I think we will see a wider uptake of AV1.
The one final point I want to add is, if you look at all our projection, 5 years and beyond, or even 3 years and beyond, AV1 is an integral part of all our mixes. So all our projections for 3 years and beyond assumes we would be doing AV1 successfully in wide scale.
Got it. All right. Well, we got a lot more questions rolling in, so hopefully we have time to get to all of them. Next up, we have, do you include memory footprint as part of the compute efficiency that you're computing?
I can take that one, Shankar. That is a fantastic question. The first versions of our study did not explicitly focus on memory footprint as such. We were primarily focused on the compute footprint, especially given the focus on ASICs, which would have generally discrete memory as we'd expected. That said, as we think about a tighter or closely knit hardware to software ecosystem where we will potentially interchangeably use software and hardware encoders, the memory both on the host and on the discrete cards becomes an increasing bottleneck, especially as we go to denser and denser transcodes. This is something we are already working on as sort of our further enhancement of the version 2 of a study. So the next round will definitely become more resource aware from a compute, compression, and even I/O perspective on that note.
Got it. And building on that, so the compute part of optimization, does that include both encoder and decoder complexity?
So currently the compute perspective we showed in the projection is only about the encoder complexity. The decoder is explicitly something we model as what percentage of decoders can actually play a particular codec. So that is separately modeled, and the compute itself only focuses on what the encoder.
So this study was more focused on sort of the transcoding at scale on the back end. It's not been as focused on the decoder throughput itself, but the decoder support has definitely been modeled.
Yeah, that makes sense. Let's see, going through these a little quickly because we have two more from the audience at least. Next up is, would having less number of video codec formats improve the power usage? It seems like supporting 3 or 4 compression formats could be increasing the power usage.
So I'm not sure I fully understand the context of the question, but if I were to hypothesize, it's probably related to the hardware design as well and the power consumption hardware blocks themselves. That is a valid question. We have not been as involved with the core hardware design itself, but it has been a major part of our discussion, though it's slightly orthogonal for this current study because it assumes given like a given transport solution and then how to model it. So it's sort of the results here feed back into how we should think about the hardware design. Shankar, you want to answer?
Yeah. So again, it's a great question. There are two aspects I want to say. One is I do think us living in a multi-codec world is a reality. It cannot be wished away, and there is a benefit of adopting advanced codecs, and there is a need to support legacy codecs for the older devices. So there's a reality cannot be wished away. At the same time, there is a case to be made for intelligent deprecation of older codecs. Do we still want to have H.264 in like say year 2030? So those are really some hard questions, hard challenges to be tackled.
Well, that's a perfect segue to the last final question we have from the audience today, which is device support the major reason to still use H.264? Regarding complexity, it seems like VP9 and other advanced codecs can also be operated at low complexity modes.
I do think, first of all, I think there is 2 parts to it. One is whether you can do it on a software versus hardware. And it's obviously you could have VP9, a software VP9 operating in a mode, which is like a lower complexity mode. And similarly, AV1 having a software decoder operating in a lower complexity mode or just decoding the lower lanes. That is actually a part we did not explicitly model in our first version of this study, but this is something we are actively modeling right now. But I do want to think hardware is an integral part as well. There are some benefits of hardware decoding where, the hardware is more a binary 1 or 0. It's not like hardware can either operate or not. And there is a reason to do hardware decoding because of due to battery and other constraints. Srinath, any thought?
Yeah, I mean, I just wanted to call out that given the vast footprint of users on our services, like we have people on the most expensive devices, and you will find the most lowest cost Android phone you can get as well. And we still try to provide the best experience there. So there is definitely a need for sustaining older codecs as much as possible. And I think that's something we are trying to actively think about how we should think holistically about support. But like the reality right now is there is a significant long tail of devices that would need sort of hardware 264 support, which is near ubiquitous right now.
Makes perfect sense. I think that the question, the assumption was correct there. It was for device support reasons primarily. All right, and that wraps up the time we have. So Srinath and Shankar, thanks so much for the great talk as well as the great answers to all these awesome audience questions. Any last words?
Thank you, everyone.
Yeah.
Thank you, everyone. I think with your support, we would like to, continue on the journey of giving great video experience to everyone in the world. Thank you again for being part of this.
Please feel free to follow up with any questions offline. We'll be happy to provide more context.
Awesome. Thanks so much. Up next, we have 2 more speakers from Facebook, Jin and Jamie, who will be talking about optimization of storage in the context of video.